Hello everyone. We are going to have the clips that going to talk about the method of virtual work, or in the author name is the unit load method. And this problem we are going to solve by using this method, which is have some advantage over the conjugate beam. As you may know, the conjugate beam is good if the load is in the form of point load, because when the force is point load, the moment on the shear is going to be in the form of rectangular and triangular. That means we can compute the area of the triangular easily. However, when the load is in the form of uniformly distributed load, the shear going to be in the triangular, and the moment diagram is going to be in the form of curve. This means we are going to determine the area and the centroid of this portion of the beam, and is going to involve with the integration of the function of the moment, and that is the disadvantage of the conjugate beam and the advantage of this method of virtual work. However, the method of virtual work have some disadvantage, such as it's going to be pretty hard to determine the maximum deflection on this beam. We got to guess the position of the maximum deflection, and then we can calculate it later. Unlike the conjugate beam, you can solve the function to determine the point of zero slope, and then you can determine the position of the maximum deflection, and then you can find the maximum deflection easier. Okay, we have the overhanging beam. It's called overhanging beam because this portion AB is overhanging, and this beam has a constant EI. Okay, and is subjected to, as I mentioned, uniformly distributed load at the point load. And then we're going to determine the vertical deflection at point C. Okay, and then you got to draw elastic curve of this beam properly. But before we go further, we should draw the elastic curve to understand what going to be the deformation of this beam. We know this is the pin, right? This is the pin. The pin allows the rotation, so this portion of the beam can rotate like this, and it's going to rotate in this direction, counterclockwise direction, because the 8 kilonewton per meter gonna push the beam down here. Okay, and then the beam gonna deflect, and then coming back to this point. This is the roller. Okay, as the pin is allowed the rotation of the portion ABC. Okay, and since the beam will be deflect, so it's gonna deflect something coming back into this portion. But how big is this is depend on what we imagine. Since the load here is 8 times 4 is 34 kilonewton, and load here is 30 kilonewton, I guess the deformation of the beam should be like this. It should be concave downward here, and then it change to the concave upward like this. I guess it's going to be like this. And we are going to determine the V sub C here. And V sub C may not be the maximum deflection. We don't know yet, but usually the maximum may occur at the midspan of the beam. And it depends the effect of the 10 kilonewton to this beam. If its effect is small, okay, the shape of the beam may be like this. If its effect is large, in which we can compute it, is maybe it maybe have the downward deflection like this. It depends. Okay, but this time we are only interested in the V sub C. And then when we use the method of virtual work, we have the virtual work equation. Virtual work equation is the balance between what's so-called the external virtual work and the internal virtual work. Okay, internal virtual work. And what is this? Virtual works in our study is depend on how the structure behave. Okay, most of the time the structure will deform by the real load, but in this study it's what? Okay, the beam gonna assume to deform by a unit load. That is the name of this method, why it's called unit load. We use unit load to produce the virtual work. Okay, and what the unit load gonna do? Unit load going to put into some specific point. For example, this is the real beam. This is the real beam, and the real beam defect at the point C like this. If this is the point C, and then you put the 1 unit load here, and then you use imagination to times this force with this displacement, will get the external virtual work. Okay, you get the external virtual work, and that is going to be 1.0, and you're going to have V sub C vertical V deflection at point C in the vertical direction, and that's gonna equal to the internal virtual work. That's R in this beam. Internal virtual work due to the real deflection here, and it's gonna time by the internal moment here. So we have the internal moment here, and it's due to what? Due to 1 point load at point C, and it's gonna time what? Gonna time all the deflection here. So it's gonna time M, okay, over EI, and then dx. Since this is the continuous function, the M is a continuous function, it's changed with the position of the beam. So we got to integrate it. Okay, so this term is external virtual work, and this term is internal virtual work. They must be equal. Okay, for the real beam, we can determine the bending moment M. For this beam, we're going to use it to determine the bending moment small m. That's due to the unit load applied at point C. Okay, by following this, what we should do is we're going to determine the function of the moment, capital M and small m. Before we can determine the capital M, determine the equation of capital M and M, we got to do what? We got to assign the coordinate. Okay, we assign the coordinate of the beam segment. How many segments do we have for this beam? For sure, it's going to be A, B, B, C, and C, D. That means we're going to have 3 segments of the beam. So the segment is going to be 3. So it's up to you how do you set up the coordinate. Okay, but if you set up the coordinate from capital M, it's going to be the same as the small m. Okay, by this way, let me put this one as the x1, put this one as the x2, and put this one as the x3. By doing this, what we have the segment. This is going to be the segment A, B, B, C, and D, C. And if you put this something like this, it's going to have the total of 3 segments. And each segment have its own length. They have its own length. What is the length of it? NGE. And the AB is supposed to be x1, x2, and xt. The x1 gonna start from A up until B. So that means it's going to be 0 less than or equal to x1 and x1 up until 2 meter. Okay, and this one from 2, sorry, let me put this one in this color. This one from 2, sorry, this one from 0 again, this one from 0 again, and it's going to be less than equal to x2, and then it's run until 3 meter. And the other one, we start from here. Again, it start by 0 less than or equal to 1, and then it's gonna equal to 4 meter. Okay, it's up to 4 meter. Now, what we have is to determine the equation of this, and then just put this one over here. We're going to have the equation from the M, capital M, and equation from the small m, and then you just put this one. Usually small m equation is short. Okay, capital M equation gonna be large, so that means we're going to put this one AB, this is AB, this is BC, BC, and this is gonna be DC. Okay, from D up until C. Okay, we have 3 parts. So now we're going to cut the beam and draw the free body diagram. Okay, this is our, actually this is the first step. We use this one, and then we cut this. What we have is just put this one down here, and this one here, and this one here, and then we have this portion of the beam. Let me put it in the back like this. Okay, this is the first portion, and then this is going to be the x1 is subjected to the force of 10 kilonewton, and the next one we have this portion of the beam, and then it's going to subjected to, this is 10 kilonewton, and we're going to try to determine the reaction down here also. So we're going to have the reaction here. Okay, and this is going to be 2 meter, and this is going to be x2. Okay, and then the last one that we have is here, and we're going to cut the beam into this portion, Okay, and by this it's going to be x3 here, start from here to here, and we also need to determine the reaction here. So First thing after this, we got to determine the reaction of the beam, and if you like, you may just put this one as the free body diagram to make things a little bit easier. But if not, you got to draw it again. Okay, let me start by drawing the free body diagram here to find the what's the so-called the reaction and the b sub y and d sub y and also d sub x here. Okay, just push this one into here. Okay, this is going to be the 8 kilonewton per meter, and this is going to be the 10 kilonewton, and what we have, this is going to be the d sub y, this is going to be d sub x, and this is going to be the b sub y, and it's going to have 2 meter, 3 meter, and 4 meter following the problem. Okay, and then what we have now is what from the free body diagram. Find the reactions, okay, from the free body diagram of the beam. Okay, we do the summation of x sub x equal to 0. What we have is what? D sub x equal to 0. If you like, you also supposed to push this one x and this one y also. So this one for sure is 0 because no applying force here. Okay, this is positive. And then you may do the summation of the what? Summation of the moment about the summation of the moment about d is 0. Take moment here. So the b sub y gonna rotate in this direction, b sub y. So we have how many? 7. Okay, 7 b sub y is gonna rotate in this direction. And 10 is gonna be in the opposite direction. 10 gonna time by the distance of 9. Okay, that is going to be in opposite direction. This is clockwise, this is counterclockwise, and this also have its resultant force. The resultant force gonna be 8 times 4. That is gonna be 32 kilonewton. So the 32 gonna rotate in the opposite direction. So you put this one of what? Of 32. And since this is uniform load, the distance here is going to be 2 meters. So this is 2. You got this 90. You got this one for 64. So the b sub y going to be 90 plus 64 is 154. And then you divide it by 7. Okay. And what you get is the reaction at b sub y of 22 kilonewton. You can check it for 22 kilonewton. And then the last one, you do the summation of f sub y equal to 0. And then you have what? You have the d sub y upward is positive. So you got the d sub y plus 22. That is the b sub y, and it's going to equal to 32 and 10. 32 plus 10. So your d sub y is going to be 42. That is 42, and then minus 22, and then you get this for 20 kilonewton. That is for the d sub y. This is 20 kilonewton. This is 22 kilonewton. And now, okay, and now you may practice to draw the shear diagram and moment diagram if you like, but we not required it here. What required here is determine the moment capital M. So by doing this. This is going to be, let me put this one in pencil. This is going to be capital 1, and actually it's going to be here. Okay, and what we have is, if you do the summation of moment equal to 0, you may have the M1 and this one gonna go together. So M1 is going to be equal to minus 10 x1. Okay, we put this one as a positive. It's going to go in the same direction. So when you move it back, it's minus 10 x1. And next, we have this as the M2. Okay, and it's has a shear here. And over here is 22 kilonewton. If you do the summation of moment equal to 0, and this one is positive, you will take moment here. So M2 and this one gonna rotate in the same direction. We have M2 plus what? Plus 10 times this plus 10 times 2 plus x2, 2 plus x2, and it's going to be equal to, this is going to be in opposite direction, equal to 22 times x2. Now we got the M2 equal to what? 22x2, 22 x2, and then you're going to move this one gonna be minus 20, and this is going to be minus, you move in opposite direction, minus 10 x2. Now you align this one with the equation of what? Of equal to this 12 x2 and then minus 20. That is going to be our M2. And if you like to highlight it, okay, this is going to be the green one. Just put this one for the green one and this one for the yellow one. Okay. And the last one, we have this portion. We have the uniformly distributed load of 8 kilonewton meter here. And also we have the moment. This is going to be for the sign convention. Okay, this is going to be for the M3. Okay, let me put the M3 over here. And if you like to put this one, the shear also support in this direction. Okay, now we do the summation of moment equal to 0. Take moment here. So the M3 in this direction. Okay, M3 gonna rotate in the same direction as SX3. It's going to go together. So M3, and it's going to plus 8x3. And since this is half of x3, so it's going to have x3 divided by 2. Okay, it's come together. However, the load here, 20 kilonewton is going to be in opposite. So this is must be what? 20 times x3. Okay, and now if you do this is going to be equal to 20 x3, and you're going to move here, this cut to be 4 is going to be 4x3. It's going to be minus 4x3 square. That is going to be the equation for this portion. Okay, in actuality, this going to include all of the equation onto this. So this is 20x3, and it's going to be minus 4x3, and then square. And the other one is going to be minus 10x1. This is x1, and this is going to be 12x2 minus 20. 12x2 minus 20. Okay, we have all of that. And that is not enough. We got to find the small m. Okay, small m sub c here. That is for the capital M. So the same thing. When we use the coordinate for this in this way, so you got to put the coordinate for this beam in this way also. So this is x1, this is x2, and this is gonna be x3. This is 2 meter, 3 meter, and 4 meter. And then you're gonna cut it the same way as we has before. Okay, so now we do the projection of this beam up into here. Okay, we do the same thing, just project it out, project it down, project it down here. You also have this one also. So this is going to be your beam to determine the small moment m. Okay, small m here. Okay, this beam is going to subjected to 1.0 force at C, and it's also going to have the d sub y and the d sub x, and d sub x for sure is gonna be 0. Okay, and then you also have this for what? For the b sub y. Okay, and then find the reaction for the free body diagram of the beam here and beam here, and then we have what for this one? We may put the summation of x sub x equal to 0. So you got the d sub x equal to 0 for first one. For the second one, you may use the summation of the moment over here at d equal to 0, and then your b sub y gonna rotate in this direction, rotate this one. And this is what? 3 meter. This is 4 meter. So you get 7 b sub y, and it's gonna rotate this way. And the one gonna rotate in opposite direction is gonna equal to what? Equal to 1. Equal to 1. And it's gonna time what? Gonna time 4. So your b sub y gonna be 4 over 7. Okay, that is gonna be your b sub y here. Okay, that is the result. And the last one, you do the summation of f sub y equal to 0. You're gonna determine the d sub y up plus. So your d sub y plus 4 over 7. This one and this one, and it's going to be equal to 1. Okay, so now you got d sub y equal to 1 minus 4 over 7. That means it's going to be 3 over 7. So this is going to be 3 over 7. Okay, that is the reaction for this beam. And now you cut it. Cut this one, and cut this one. And then it's going to be very easy for this. This is going to be the x1, and you can see there is no forces. Okay, and then what we have is the m sub c1 equal to 0. Okay, there's no forces. And then the second one, you're going to cut to here. And now what we have is you have the b sub y. So this is going to be 4 over 7. And this is going to be x2 up to here. And now you have this one is going to be m sub c2. Okay, this one m sub c2 is easy. if you do the summation here, this is going to be equal to 4 over 7 and time x2. Okay, very simple. You may use summation of moment equal to 0. You get this. And the last one is here. And this is going to be x3. This is going to be x3 from here to here. And what we have here is the direction. See, we always use the same direction as the sign convention that we have using it since the ending static. Okay, this is going to be m3. And what we have here is 3/3. The first here is, sorry, 307, not 3/3, 307. So if you summation of the moment equal to 0 here, okay, you may take the moment here. Now um3 is going to be equal to 3 over 7 and time x3. Okay, now you got 3 more equation. That is for the m3, small m3, and that is for the m1, m sub c1, small m sub c, so m sub c2, this one, and then you put them over there. So this is gonna be 0. Okay, and next is going to be 4 over 7 x2, and the last one gonna be 3 x3 over 7. Now you have all you need to, which is the equation for the capital M and the equation from the small m sub c. So you can put into this equation and integrate it from start of x1 to n of x1, and then plus start from x2 to n of x2, and then plus start from x3 to the n of x3. So by doing this, let me do the calculation over here. Now we have 3 portions, and since we have 3 portions, we 1, 2, and 3. Compute the v sub c. We compute the v sub c. So we have 1.0, and we have deflection at c in vertical, and it's going to equal to 3 of them. The first one, the integration of this and this. So we do just put it, actually it's 0, you don't need to put it, but I like to do it for the completion of this. This is going to be minus 10x1 times 0 dx1 over ei. Okay, that is the first portion. And then for the second portion, you may plus this one, plus, and this one is integration from 0 to 3, from 0 to 3. And this is going to be 12x2 minus 20 and time 4 over 7 x2, and this is dx2 over ei. Okay, this ei is constant. If it's not, you just do it by just put the number, okay, over the ei. And then the last one plus the integration, this time is here up until here, this time from 0 to 4. And we have this one for 20 x3 plus 9 minus 4 x3 square, and then 3 x3 over 7 and dx3 over ei. Okay, that is we have. And finally we arrive at what? this is going to be 0, and this is V sub CV. This is, you do the integration, is up to you. If you have S1 calculator, just do it. If not, you need to do it by your hand. Okay, I will allow you to use any calculator that's specified from our school. That is Casio 8000 series, 9000 series, or Algebra 1 or Algebra 2 is up to you. So you get this for 10.29 over EI. This is plus, that indicate that it go by the direction of 1.0. That means it go downward. Okay, and then the last one we have is for plus 23.14, and then what we have is divided by EI, and finally you got this for 83.43 over EI, and it is downward. Okay, as you assume it in this direction. If it's negative, it's going to be opposite direction. If it's positive, it's in this direction. Okay, and since they have to ask us to determine what the E is 200 gigapascal and I is 110 power 6. So we do the calculation by the kilonewton. So the E that's used to be 10 power 9 Newton per square meter. So it's going to be 210 power 6 kilonewton per square meter. We're going to use this. Okay. The I here must change to meter power 4. So it's going to be 110 power 6. And it's going to divide by 12 because 10 power 12 millimeter power 4 is equal to 1 meter power 4. So this is going to be 110 minus 6 meter power 4. If you have this, you just plug it in here. So we will have the deflection of this beam equal to 83.43 divided by 210 power 6 kilonewton per square meter, and you gonna time it for 110 minus 6 meter power 4. And if you push everything in the calculator, you may get this one for 4.17 and 10 minus 3 meter, or 4.17 millimeter. If you like in millimeter, you may put it like this. Okay, and then if you also like, we can do some practice to draw the shear diagram and moment diagram of this beam. Okay, and this is going to be the information that you may use the conjugate beam to check your answer. If you like to draw the shear diagram, moment diagram, you got to put things very clearly. Okay, now what we have is what? Shear diagram. Okay, and that is going to be X meter, and this is 0, this is 2, this is 5, and this is 9, and this is going to be the V kilonewton. What we have is, we move from the left to the right again. We have what? We have 10 kilonewton. So what we have is going to be 10 kilonewton. Let's say it's downward. Okay, so it's going to be minus 10 kilonewton. And again, what? There is no distributed load. So the dV by dx equal to 0. So this one gonna be constant. This is minus 10 kilonewton. and then it's taking up by 22 kilonewton. So this one gonna take by 22. I use the scale. Okay, 10 is 5 millimeter. So 22 is going to be 11 millimeter. Okay, that is going to be minus 10 plus 22. That is 12 kilonewton. And then there is no distributed force here. So the dV by dx equal to 0. You get this as a constant. And this is going to be 12 kilonewton. And now you arrive at this. dV by dx is going to be minus 8. So the dV by dx is going to be minus 8. And it's going to be downward, right? Sure, it's going to be downward. And you know the reaction here is 20. So it's supposed to be downward up to here, 10, 20. It's going to be minus 20 kilonewton. And this 20 kilonewton gonna close here. Okay, that means you know that your graph gonna be something like this. Okay, and this is going to be the slope of your graph. If you like to, no, you need to keep this to clarify what you compute. And what is this? You can determine by similar triangle. Okay, it's going to be 12 divided by x. So it's 12 divided by x. And it's equal to slope. Slope of what? Slope of 8. Okay, so your x is going to be 12 over 8. Okay, that is going to be 12 over 8. It's going to be 3 over 2. No, 12 over 8. 12 over 8 is going to be 1.5. Okay, 1.5 meter. Okay, 12 over 8 is 1.5 meter. And then you may go further to draw the moment diagram of this beam. Okay, let me put this one here. And this is going to be the moment kilonewton meter. And again, we got this for 0, 2, and plus 3, 5, and 9. This is going to be meter. And there is no external moment. When it's no external moment, this is going to be 0 kilonewton meter. And this one also 0 kilonewton meter. There is no external moment. That's not the moment diagram is 0. And then what we have is the shear is minus 10. So the dm by dx gonna equal v. So it's gonna be equal minus 10. And then what we have, what's going to be the shear here? That's to be the moment here, sorry. Moment there is moment what? This is point B, M sub B, and then minus 0 is gonna equal to the area under shear diagram. Okay, that is gonna be what? 2 meter, like this is gonna be A, B, C, and D. This is going to be minus 10 and then time 2. So the M sub B is going to be very easy to determine. M sub B is going to be minus 20 kilonewton meter. So it's going to be minus 20. Let's put it 10, 20. And it's going to be the straight line. Okay, that is minus 20. This is the slope, this is the slope, this is the slope, it's downward. So it's going to be minus 20. And then the slope just change into the positive. You may see the slope now is positive. And you may put this one. What? You're going to determine the moment about here. Now we have m sub c, m sub c, minus here, minus of minus 20, that's here, m sub c minus b, and equal to the area here is 12, and then time 3. So your m sub c gonna equal to, this is gonna be 36. This is gonna be plus, when it's moved back, it's going to be minus 20. Okay, and you're gonna have this for 16 kilonewton meter. That is going to be 16. So it's about 8 millimeter. And now this one have the dm by dx equal to plus 12. And we have this for, this is what, 16. Okay, and then you put this one for the slope. And now the graph will be go up like this. Since the shear here is 0, so the dm by dx here is 0. Slope is 0. Okay, the m here, the m here, minus what? Minus the 16. Minus 16 here. And it's going to be equal to this triangle. Okay, and it's equal to 1/2 of 1.5 and times 12. So the m is going to be, this is going to be 6 times 1.5. So this is going to be 6 times 1.5. That is going to be 1.5 is 3 is going to be 9. Okay, and then it's going to pass 16. And this time it's going to arrive at what? 25 kilonewton meter. So we have 25, we have this, we have this. Okay, it's going to be up for 25. That is going to be 20. Okay, 10, 20. 25 is about this. This is 25. And your graph going to be curved since the slope change from the 16, okay, to 0. So it's not curved like this. And finally, since this is 0, it's going to curve downward here. And you got this for dm by dx equal to minus 20. Okay, now you arrive at this point. This point is 0 moment. What the 0 moment tell us? 0 moment telling us for the position of the inflection point. So if you follow this, your beam, you can sketch up the beam deflection, okay, more properly than before under the uniformly distributed load by using appropriate scale here. Okay, this is going to be the inflection point of the beam. That's going to change the curve, okay, from upward to downward. So the curve supposed to be something, and then we have this is for 4.17 millimeter. So this is gonna be, this is point C. Okay, this is gonna have, let me time is 2 times. It's gonna be about 8 point something millimeter. So it's gonna be something like this. And this is going to be the inflection point. And this one gonna be the V sub C equal to 4.17 millimeter. And we don't know this one yet. We can determine it. This is going to be theta sub A, B, C, D. Okay. And next, I believe this one have a small moment compared to this one. So I think this one's supposed to be up like this, and it's going to curve like this. Okay, and this one gonna be the theta sub b. Left and the right going to be the same thing, theta sub b. And this one gonna be the phi sub a. And the slope here, if you like, is gonna be the theta sub a. The real value here can be determined, but up until you get this value, you are not sure it's going to be upward, downward, but this is just what I'm guessing. And then next, what we can do is, if this one is not the steel beam, but if this one is the RC beam, if different RC beam, okay, you may put the reinforcement onto this beam. Usually this beam have their own reinforcement all around its length, okay, to make the cage of the beam. But due to this, what we have, this is the positive, okay, so most of the time you got to put the reinforcement here for the concrete to taking care of the tension, and you're gonna put this development length, let's say this is hook, usually it's hook, and this is going to be development length, okay. Ajahn who teach RC to you, they will explain to you, we have this to and a hook over here to what, to make the steel attach to the concrete completely, okay. And on the top you may have this also, okay. That is the additional reinforcement to make the beam to resist the force more properly. So you, as an engineer, is your duty to compute the area of the steel and the area of the concrete after you get the analysis result. So the maximum moment is going to be Mmax is going to be 25 kilonewton meter, and Mmax negative Mmax is going to be plus, and Mmax negative is also minus 20 kilonewton meter, because Mmax negative going to use to determine reinforcement here, Mmax positive you're going to use to determine the reinforcement here. And for the shear diagram, the shear there you're going to use to determine the also called the stirrup, okay. This is going to be the stirrup, this is stirrup, okay. And if it's large, the stirrup gonna be more frequent or more than the smaller force, okay. This is going to be have a smaller s spacing between the stirrup, and then you also have to put this one stirrup, and then when the shear is small, you may put the spacing is larger. So this is supposed to be the draft steel reinforcement for RC beam, okay. This is going to be what we call it is going to be the elastic curve, okay. Elastic curve of the beam. It have inflection point here is important, because inflection point telling us the point that we change the reinforcement, and this is going to be the M diagram, and this is going to be the shear diagram. Okay, this is for the review of this, and then I connect what we study to what will going to be in the design of the RC beam. For the steel beam, it's going to be straightforward. You can use the max here, only this value to determine the section and check with the maximum shear. So the Vmax is going to be minus 20 kilonewton. Okay, that is all I have for this clips, and this is the kind of the beam that we should be able to analyze this. Okay, when you analyze this, that means you can find the reaction, you can draw the shear diagram, you can draw the moment diagram, and also you should draw the elastic curve, and finally you should be able to put some detail on what it should be when the beam going to reinforce with reinforcement. Okay, that is the chapter. Oh, sorry, this is the clip for the method of virtual work or the unit load method. Okay, bye bye.